This is just another tool that you could use. It greatly streamlines the work, though. So that's your motivation for actually learning it. Uh, any situation in which you see the words "at least one" would follow this rule, and that's because if I were to, I'll just create a list. Let's say we have a list of just 1, 2, 3, 4, 5. List of 5 values. Call these X values. If I want at least one, right, at least one of these values, I could do it this way. I could have just a 1. I could have 1 and 2. I could have 1 and 3. I could have 1 and 4. I could have 1 and 5. So any one of those possibilities would come into play. It could be 1 and then some other outcome. If I'm again, this is for multiple events, so I wouldn't just take one of the values. I would take many of the values. So it could be the case that I need to select 4 of them at random. What's the probability of getting at least 1, 2? Now, from that set, it's a little bit of a different story. I would have to think of the different ways that I could have a number arrangement from this set in which a 2 is involved at least one time. So again, just a scenario to kind of jazz it up a little bit. I would say I'm selecting 4 values. We want to know the probability of getting at least one of them to be a 2. All right. What that would mean, and we're not going to get into the probabilities yet because it's too hard without learning some of the other things that go along with this unit. So we'll kind of dial it back. But this is what it would be talking about. It would be saying, all right, I'm selecting 4 of these numbers at random. One 4-number selection could be this: 1, 2, 3, 4. Maybe it could be 1, 3, 4, 5. Maybe it's 2, 1, 3, 4. Maybe it's 2, 1, 3, 5, and so on. So a whole bunch of possibilities. A way to handle it, I mean, if you're ever in a jam, you could list out the sample space if it's not too large, but I'm looking for any case that has a 2 in it at least somewhere. At least one of those numbers has to be a 2. That happens so far here, here, and here. It does not happen in this one. I don't have a 2 in there anywhere. Right? So what we need to do is somehow come up with a way in which we can not have to list out all the possibilities in order to figure out what the solution is. And this example that I made up on the fly actually does a good job of that, because what's going to be easier to identify? The cases that satisfy the at least 1, 2, or the cases that don't? The cases that don't are less numerous. All right? I have, just on this, I mean, there's many more possibilities, but just out of this list here, I had one way that didn't work, but 3 different ways that did work. So if I could figure out all the different ways in which it doesn't work, so I would find the probability of getting no 2s. So this is what I don't want. All the stuff I don't want. The complement rule that we talked about last class tells us that if I don't want a particular set, remove it from the total, and whatever will be left over is what I do want. So I would subtract this from 1, and that would be the same thing. So harder to find all the instances in which I would have at least a 2 in there somewhere. It's easier to find the cases where there are no 2s in there whatsoever. So find the cases that don't involve 2, find that probability and subtract that from 1, and whatever is left over must necessarily be what you're looking for. right? But that example, that's kind of what we're working towards rather than where we would start. But it gives you a good sense of the idea, hopefully. And if not, the next three examples will. Find the probability of tossing at least one head in two tosses of a fair coin. So probability of at least one head in two tosses. All right. I really want to emphasize the at least one head part of it. All right. So we're tossing a coin twice. Yeah. So that's not a crazy amount of outcomes. I could actually list the sample space: heads, 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 tails, tails, heads, tails, tails. Those are the different ways I can flip a coin twice. Sample space. You could go tree diagram. Heads, tails. After I get the first head, the second one could be a head, the second one could be a tails. After I get the first one, if the first one's a tails, the second one could still be a head. The last one could be a tails. So whether it's sample space or tree diagram, we get an idea of what we're looking for. So if I need at least one head, that's telling me that maybe just one of the two outcomes are heads. Maybe they're both heads, but there has to be a head in there somewhere. The cases that involve heads being there somewhere are these three out of four possible outcomes. You could look at it this way. If the first outcome in a tree diagram, if the first outcome is your set of heads or is a head, then anything in this category would work. So then I would just have to focus on any other situation that might also play out. All right, so that's also 3 out of 4. Yeah. So 28? Yeah, 28. Good enough? Unless you're enjoying this. You're running back and forth.
Professor, you know that I print out mine, but I didn't realize that I had a 5th page, and it came out so tiny. I print out like 27 pages.
27 pages of like mini font. Well, you got plenty of room to take notes, I guess. So these are two ways that you could figure it out, but you already see the drawback with this. If the outcomes are too numerous, then this is not worthwhile. If I were to say 2 tosses of a coin, 3 tosses of a coin, that's fine. But if it's 30 tosses of a coin, that's a pretty large sample space. Right? Change it over to dice. I mean, even 2 rolls of a die, that's 36 outcomes. That's a lot of stuff to write. Right? So we want the formulaic approach to kind of bail us out on that. So at least one head. So probability, at least one head. That's going to be equal to 1 minus the probability of getting, well, it says 1 minus probability of none, but none in this case would be no heads. In almost every probability question, there's a thinking step. That's, I think, what makes probability hard, because when you're tackling most other math problems, it's follow the steps. If you do this and that and that and that and that, you'll get the answer. And that's really all there is to it. Your challenge is to remember what the steps are, and under what circumstances you use them. Here it's know all the steps, that's great, but there's one component in there that you're going to have to address just by thinking about it, and that's what makes it a little tricky. So probability of no heads, we want to think about what that means. I'm tossing a coin twice. What that's telling me, and I'll write an intermediate step here, but it's telling me that I'm not getting a head the first time, and I'm also not getting a head the second time. All right, so two things come from this. One, and means multiply. All right, so that's important enough. But also, the not heads means something else too. If you flip a coin and it's not heads, what was it? Tails. So this is the same as saying probability of getting tails and tails. You could continue on in this problem without that little bit right there, because you could just say, well, which ones of these cases don't have heads in it, you know? So you could still reason it out, but it's probably not the best way to go. Now, these are two independent events, because no matter how many times I roll a die, flip a coin, those are two cases. I'm trying to think of a third one, because you should always give examples in groups of three. Marbles don't work, cards don't work. All right, so a 6-sided die and a 12-sided die. That's my third example. I don't know. Like just something where the probability wouldn't change. We can just simply multiply. 1 in 2 chance of getting a tails on the first flip, 1 in 2 chance of getting a tails on the second flip. All right. So bringing down my 1, I'm looking at 1 minus this product. So 1 minus a quarter, 3/4. If I were in your shoes, I'd say, well, screw that. I like the other way better. But again, only for this problem, this type of problem. The sample space was small enough. Sample space gets bigger. You may not want to do it using what I did on the left. You might skew towards doing it the way I did it on the right. All right. So in the next one, we're looking at 3 tosses of a coin, still like right on the edge of what you're willing to write out in terms of a sample space. Heads, 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 tails, heads, tails, heads, tails, heads, heads. All right, we can do tails, tails, tails. I'll do it here. Tails, tails, heads. Tails, heads, tails. And heads, tails, tails. All right. When you flip a coin 3 times, you're looking at not just, you know, for the meat of it, you know, the heads, 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 tails, 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 those are obvious, I think. The other ones, I mean, it's more expansive the way they're arranged, because you could have cases where the heads outweigh the tails, but you could also have cases where the tails outweigh the heads. So
in the problem above, where you put like a probability of squiggle on H, that's like not H, right?
Mm-hmm. All right, so at least one head's using this idea. Well, any case that involves a head in some way is going to satisfy that. So there's 8 outcomes in total. 7 are what I want, so 7/8. That's wonderful. If it's 4 tosses of a coin, that's 16 outcomes. Then 32 if it's 5 tosses. 64. It starts getting out of hand pretty quickly. And the next example really gets at that idea, so we'll cross that bridge in a minute. But probability of at least one heads. Same deal. It means 1 minus the probability of not getting any heads at all, which in turn means 1 minus, well, I don't want heads on 3 separate occasions, which means I want tails on 3 separate occasions. So I'm looking at probability of getting a tails times the, I'll go capital because I did capital everywhere else. Probability getting tails probability of getting tails. I guess I don't need the open parentheses. It's not an order of operations thing. All right, so that's talking about what I did over here, this transition. It's just, it's not 2 tosses anymore, it's 3 tosses. All right, so then I'm looking at, and I'm just going to write it like this. This next step you probably would never do on a test or maybe even on your own homework, but I'm going to write it just to talk about it. But it's telling us to take the probability of getting tails and raise it to the 3rd power. All right, that's important. That's an important realization if you do have a situation that's way more complicated. All right, so if I'm going to the, or if I'm tossing a coin 13 times, I now have a model that's going to work because the first one was the same idea. It was 1 minus the probability of getting tails raised to the 2nd power. By working in smaller increments, a question says you're flipping a coin 30 times. Well, I would say, well, let's just start off with 2 times and then 3 times and see what's going on. Because by making this recognition, I now have a shortcut that'll get me the probability of getting at least 1 heads no matter how many times I flip the coin. Right? Just to clean it up, though, it would be 1 minus 1/2 cubed, which is 1 minus 1/8, which is 7/8. But if I needed to do, and this is the first time I've ever been inspired to actually add this in. New example. We'll take it as a typo. So if somebody wants it, you got it. All right. I thought my phone would be buzzing like crazy, but hold on. All right, so the new example. Probability of getting at least 1 head in 37 tosses of a fair coin. Say it again. New example, yeah. No, unrelated completely. So we're looking at, based on what we learned in the last 2 questions, the idea that I just need to find the probability of the thing I don't want and raise it to some power, whatever the appropriate power is, and that's the number of trials. So in this case, it'd be 1 minus 1/2 to the 37th power. And at that point, we'd call it, because I don't know that that's something the calculator can even handle. Maybe it can. It's a fraction to that high power, so it might be all right. But once you start getting heavy duty in terms of the powers, you can leave it in terms of the powers because it's going to be more efficient anyway. I mean, just the idea that it's going to say what, 0.999999999, whatever, something like that. And then what do I round it to? 0.9 repeating. Well, it's not really that. Technically, it would round to 1, but it's not a certain event, so it's not that. This notation is better. All right. Also, you might have noticed that your chances of getting at least a head, a single head, is all you would really need. But maybe they're all heads. Maybe it's kind of an even mixture of heads and tails. But your chances of getting that heads improves for each additional trial. Just think of it this way. You flip a coin 50 times. If I were to say to you, I'll give you $100 if there's a heads in there anywhere. You're gonna be like, I'll take that bet. Like, you're stupid. Like, you're flipping it 50 times. They'd all have to be tails. Each of the 50 attempts would all have to be tails in order for that to play out in the favor of the person asking the question. So, increase the number of trials, you increase the chances of getting at least one outcome to be the way you want. It doesn't increase your chances, however, if you needed to have a certain number of heads necessarily, because if it's like 50 attempts and you need to have more than 50% of those attempts be heads in order to win the game, I mean, it's just as likely that you'll lose. So, but in this situation, at least you know the chances are improving. This is like, and we'll get to it later, I think, maybe next time, but it's the birthday question. It's it's basically along the lines of two people are in a class. What are the chances that they have the same birthday? You'd be like, not good, right? If you go into one of the lecture halls and there's 300 students in there, what's the probability that any two of them would have the same birthday? Better than it was before, not necessarily guaranteed, because there is some chance still involved in that, but it's at that point where he's like, oh, there's 300 people in here. Somebody has to have the same birthday as somebody else. There's just so many people. Now, if I have 400 people in the classroom, then it's guaranteed that there's going to be multiple birthdays, because the worst case scenario after 365 trials, at 365 people, worst case scenario is they all have different birthdays. But once you hit that 366 person, it has to match one of the first 365. Right? So that's the thinking part of probability that can be really cool and exciting and engaging, but it could also be like, oh hold on. Where'd the 365 come from? That's, again, the number of days in the year. But, it's that kind of thing where it's like you're not thinking about the situation. You're like, here's a number, I write it down. Here's a number, I write it down. Try to think about why you're writing down the numbers that you are. Okay? A die is rolled 6 times. Find the probability of rolling at least 1 4. Sure. For the exponent?
Yeah.
Oh no, I designed the problem to have 37 tosses, so that would match. Yeah, if I said 50 tosses, the power would be 50. It's whatever it's stated. All right. So a die is rolled 6 times. Find the probability of getting at least 1 4. So probability at least 1 4. So that would be 1 minus the probability of getting no 4s. Which in turn would be 1 minus the probability of the first one not being a 4 and the second one not being a 4 and the third one not being a 4 and the fourth one not being a 4 and the fifth one not being a 4 and the sixth one not being a 4. All right, so instead of that, how about, since I'm going to write the same thing multiplied 6 times, write it as probability of not getting a 4 raised to the 6th power. All right, so we are generalizing here, and it's pretty nice because the relationship that worked for coins is still working for dice. So at this point, you get the idea that all I have to do is find the event that I'm not being asked about. So everything else, they want at least 1 4, so I want the cases where there aren't any 4s whatsoever. Figure out what the probability of that would be. Just one attempt to not get a 4 when you roll it down, and raise it to the power associated with the number of attempts within the experiment. Okay, so probability of not getting a 4 on a 6-sided number cube would be 5 6. So 1 minus Is it 3125? Over 7,776? That one I would even be surprised myself if it were correct. For those of you who are the opposite of tech savvy, I don't know what is that? I got rid of the key press history. All right, well, that's not helpful. Okay, apparently that's view cubed for whatever reason. All right, let's see how wrong I was. 5 to the 6th power. So when you're doing a fraction raised to a power, it can be tricky. Sometimes the calculator, for whatever reason, just spits back a decimal answer and then refuses the math bracket. When you're finding a fraction raised to a power, just take the top, raise it to the power. Okay, not even close. And then take the bottom and raise it to the power. Yeah, not even in the right neighborhood. See, I'm not even there yet with all of my problems. 15,625. And then 4,6,656. I just want to check something real quick. Because I think I might have taken 625 and multiplied it by 5. That's what I did. I don't know where I got the other one from. 216 is 6 cubed. Maybe I multiplied it by... No, times 6 again. Yeah. It's a disaster. Fortunately, we have calculators, though. All right, so this is not... I mean, it's an answer. It's not the most meaningful one. If we want a cleaner answer, what I would do is make a common denominator. And then subtract. So 4,6,6,5 meh, minus 1, 5 meh, meh, and meh. Got all my mehs in the right place. 31,031 is the numerator. All right. So let's see if the calculator can handle it if you use the right function, the alpha y equals. So 1 minus, so I'd go back to this one. I wouldn't do any of this stuff if I'm trying to do it on the calculator. Alpha y equals n over d, 5 over 6, close them up, and raise it to the power. I don't know why, because then, yeah, you do it like that, and even on the newer ones, it still falls apart for some reason. I'm just curious of something real quick. I don't think that this matters at all, but in terms of what the calculator is going to do, the programming on the calculator is so weird that it wouldn't shock me if this was about to work. Get rid of that 6 now. You wouldn't think, but yeah. So another way to go, so if you have to do it by hand, because if I need a fractional answer, I need a fractional answer, but you could do it like this. So you have 1 minus 5 to the 6th over 5 to the 6th. Instead of getting into the messy numbers, get your common denominator now. 6 over 6. Yeah. That would have been a really easy problem. So 6 to the 6th over 6 to the 6th minus 5 to the 6th over 6 to the 6th. And then put that in your calculator. Just typing this in will give you the numerator, and that would give you the denominator. So, I mean, everybody has their own strengths and weaknesses. There are people that didn't like this approach that think this is all right. There are people that don't like either approach. I understand that too. You'll still have to get a single answer. Now, it may involve rounding and decimals, that's fine too. But for probabilities, there's usually a nice fractional answer somewhere. On a test, just be mindful of the instructions.
To use either or would be okay.
Yeah.